All right, well, recently we were talking about the boundary conditions and boundary value problems, and soon we're going to apply the conditions and those types of analyses to resistances and capacitances. We're going to calculate the resistances of non-uniform conductors. If you recall, we already looked at resistors for uniform conductors, and we're also going to apply these ideas to calculate capacitances of materials. So we haven't even looked at capacitance really yet. But before we do that, I just have just a couple more fine points to say about boundary conditions in the context of what's called Laplace and Poisson equations. The idea is that it's usually not known what the charge density or the potential is throughout a region in space whose electric field we want to know. Laplace's and Poisson's equations can help us find the electric field when only charge or potential is known at the boundaries of material. And it's usually the potential that's known at the boundaries of the materials. All right. Now, I've got some notes here, but we'll get to those notes in a second. I want you to recall a couple things. First of all, that we've got the divergence of E is equal to the charge density divided by the permittivity. This was coming from divergence of D is equal to rho V. That was one of our Maxwell's equations. And then related to the electric field is that the electric field is the negative gradient of potential. Now if I put these two things together, then I've got the divergence of the negative gradient of V. And the divergence of the gradient was called the Laplacian. Do you remember that? In our study of vector calculus, and we used del squared to represent the Laplacian operator. Okay, so this is one of the equations that I want to talk about. That's called Poisson's equation. All right, and then if it happens that the charge density or the charge distribution is zero, so rho v is zero, then we have the Laplacian of v is equal to zero, and that's called Laplace's equation. So this is Poisson's, and this is Laplace. Laplace is a special situation, and Poisson's is the more general situation. All right, and then just to remind you that the del squared operator, or the Laplacian operator, can be expressed in Cartesian, cylindrical, or spherical coordinates. We already looked at that, but just to remind you that that's coming, or you should have that in your notes somewhere. Now, just a few points of solving these equations, because they're essentially the same equation. It's just that the right-hand side may or may not be zero. So here, observe my notes that I've got written for you. So in these equations, it's the voltage or the potential difference that's the unknown, and these guys are second order partial differential equations because the del operator is like the derivative, right? It's a vector derivative, and so taking it twice is the second order. So you can solve these differential equations then with integration. So point one here is that you can find a non-unique, i.e. with constants of integration, by straightforward integration of a function of one variable, or a separation of variables if v is a function of more than one variable, like x, y, z. All right, and again, so you integrate twice, right? So you're going to have multiple constants of integration. And then point two, and that's what we mean by non-unique. The constants of integration are there. Now point two, then we're going to apply some sort of boundary conditions, some conditions that we know to find those constants of integration, and then that fully specifies the potential V. So in differential equations class, you would have seen like a dynamic system where the unknown is, or the variable is time. And so when you integrate, you're given an initial condition, right? Initially, at time equals 0, what is the state of the system? So our variables are space, x, y, z, and so we don't have this thing called initial condition. We have, give me the condition at a boundary in space. So you can think of boundary conditions as being like your initial conditions. Now point 3 then, with V fully specified, we can find the electric field by noting that the electric field is the negative gradient of V. And then we can get the electric flux density if we want, being that that's epsilon times the electric field. And we can also get the current density if we want, being that that's the conductivity of the material times the electric field. And then point 4, if it's required, we can find Q induced on a conductor, the charge induced in that conductor, with Q is equal to, and then we integrate over the surface of the surface charge density, noting that the surface charge density is equal to the normal component of the electric flux density. And that came about in the previous video when we talked about boundary conditions. On a conductor, the surface charge density is equal to the normal component of the electric flux density. And then the current in the conductor, I, can be found using the definition of I and current density by integrating the current density, the dot product of the current density with a differential surface area. All right, so we're going to put these into practice now. I've got several example videos coming your way. And then after that, we're going to apply these to calculating resistances and capacitances, to fundamental concepts in electrical circuits. So I will see you there.